Hello everyone, my name is Minho Huang. In this video, we are going to present our paper about applying depth sensing to automated surgical manipulation with a Da Vinci robot. This is the outline of the presentation. After the ISMR paper was accepted in January 2020, we continued to work on it, and the subsequent paper was submitted and accepted to Robotics and Automation letters in July 2020. We'll give an overview for the extension of this work at the second part. Robotic surgical assistants, such as Da Vinci robot, are widely used in hospitals and surgical procedures using teleoperation. Although surgical robots has a long history, no procedures are fully autonomous due to uncertainty in perception and control. In non-clinical research setting, several research groups have explored automating surgical robotics. Key applications include cutting gauze, debridement, and surgical suturing. In this paper, we focus on the PEG transfer task, which is one of the standard tasks in the fundamentals of laparoscopic surgery. To the left, we show how the task proceeds under a human operator. The human picks a peg from the left side of the board, hands it over, and inserts the peg on the other side. To the best of our knowledge, the only other prior work from Rosen and Ma attempts to automate a variant of the peg transfer task, which is moving 3 blocks to the neighbor pegs. We build upon this pioneering work to achieve a full completion of the task. For our method, we select a ZV-1 Plus depth camera. Depth sensing has been increasingly available with its high visual perceptual capability, including accurate 3D object detection using its dense point clouds. It would be possible to apply the depth sensing to open surgery robot, such as Taurus from the SRI. The PEG transfer setup using the Da Vinci Research Kit is shown in the large figure here. We install the depth camera over the scene by roughly 0.9 meters. We use 6 triangular blocks and paint them red to simulate surgical environments, shown in the figure below. Cable-driven robots has imprecision from cable-related effects, such as cable stretching or hysteresis. Since the PEG transfer task requires high precision, we calibrate the positions by using a checkerboard. We manually move the robot to each corner of the checkerboard and record the positions. During deployment, we map the given image pixels to a 2D coordinate on the checkerboard and then convert it to the recorded position of the robot. The RGB image of a starting configuration of the PEG transfer is shown in Figure A, along with the corresponding depth image in Figure B. We use depth masking to find a pixel point on the blocks. Then, perform cross-correlation with a known shape template to match the pose of the blocks. The last figure shows the 12 detected pegs, along with the 6 grasp points and 6 place points, which are circled in white. The depth camera creates a strobing effect. As a warning, please watch out for flashing light in the videos. Here, we show an example of successful trajectory at 4 times speedup. We define one episode of the task to be the full procedure, where the robot moves the 6 blocks from the left to the right, and then transfer them back. In this case, we get 12 out of 12 block transfers. Here, we show some failure modes. Peak failure occurs when the gripper touches the block edge due to the tip positioning offset from the block side. The vast majority were placing failures. Placing is challenging because the orientation of the gripped block is affected by the pickup accuracy. On the left, we show place stop, where the dropped block touches a block underneath. We had 17 out of 31 failures. The place fall failures on the right resulted in the bottom of the block making contact with the top of the peg. We had 11 out of 31 failures. We compared the results with the human surgical resident. As shown in the first table, he achieved a success rate of 95.8% and 83.3% with a single and bilateral arm respectively. He did not experience any full failures, but had 1 stuck failures with a single arm and 4 failures including 1 pick, 3 stuck in the bilateral case. The proposed approach achieved a relatively low success rate. Humans complete the task twice faster with the single arm and 1.6 times faster with the bilateral arm than the automated system. In the second part, I would like to introduce a subsequent result as an extension of this work, which is titled Efficiently Calibrating Cable-Driven Surgical Robots with RGBD, Fiducial Sensing, and Recurrent Neural Network. This work is published in Robotics and Automation Letters. This method used the combinations of depth sensing, 3D printable fiducials, and recurrent neural network. From this method, we could get accurate measurement of robot state, identify the source of error, and attain high success rate of peg transfer using online correction of joint errors. We print 6 fiducial spears and strategically attach 2 spears on the tool shaft and 4 spears on the jaw. We obtain 3D position of the spears by masking depth and color in the point cloud. Then we could estimate 6 joint angles based on the DVRK kinematics. The accuracy of the measurement as a result is 0.32 mm in spear detection, 0.6 degree in joint angle estimation. During error identification process, we compare the commanded configuration with the measured. We found out that the last 3 joints are the main source of error since they are highly coupled with hysteresis. As shown in the video, we collect 2,000 data pairs, which consisting of commanded and measured joint configuration. Given the data, we train 13 different models based on its architecture, input, and output format. We use the long short-term memory to capture the cabling effect from the history of the robot motion. We evaluate these models on the online fiducial free state estimation. As shown in the table below, the best model reduced the mean tracking error of the physical robot from 2.96 mm to 0.65 mm. Finally, we evaluate the performance of the best model using surgical peg transfer. As a result, the robot achieved a success rate from 39.4% without calibration to 96.7% with calibration, which is comparable to performance by the human expert surgeon. The speed of the transfer, however, is still twice slower than human operator. As a conclusion, we explore the potential for depth sensing. We demonstrate how using a depth camera and calibration can be used in automating the surgical peg transfer. The extension of this work showed efficient and autonomous calibration methods using a 3D printable fiducials, and the final model attained higher positioning accuracy with a success rate comparable to the human expert. In future work, we will focus on failure recovery, handovers, visual surveying, and trajectory optimization. Please check out our project website for additional information. Thank you for watching.